Hi, everybody. And as promised, we're going to continue and we're in theorem 2.5, which deals with the number of solutions to linear system. This is a fact that we've always known in high school, that when you do a system of linear equations, you always get either one solution or you get infinite solutions or you get no solution. This is something we've known for many years, but we really had no way of proving it, or we never did prove it. I shouldn't say no way, but we didn't ever prove it. And now we can actually do the proof of this amazing fact that we've known forever. We can actually do it relatively easily now that we have the equipment, some of the equipment that we've built up in linear algebra, which is one of the many reasons why this is so awesome. So here's the proof. First thing we're going to do is we're going to write the system in the form AX equals B, meaning where A is the coefficient matrix, X is the column matrix of the variables, and B is the column matrix of the constants. And that's something we learned, that you could write a system of equations in that form, and it has the same meaning as the system of equations. And because AX equal B is only true if the solution of those linear equations, the solution of that system is all true. Anyway, if the system has exactly, now here's a very clever way of looking at this. If the system has exactly one solution, or if it has no solutions, then that's it. There's nothing to prove. So what we want to do, this is a little subtle, and we want to assume that the system has two solutions. And we're going to call one of them x1, the other one x2. Now, x1 could be like, let's say it's a 3x3 equation, a 3x3 system. So x1 could be 9, 12, 4, and x2 could be 17, -30, 8, or something like that. Meaning like two different points of solutions. Anyway, if you show that this assumption will automatically imply that the system has infinitely many solutions, then the proof will be complete. So that's what we want to do. So what we want to do here is we want to show that if there's no solutions, fine. If there's one solution, fine. But once you have two solutions, that's going to force you to have infinite. And that's really what the theorem is saying. There's only three choices: no solutions, one solution, or infinite solutions. So here's how we're going to do it. Now, because x1 and x2, again, these are vectors. These are column matrices of solutions to the system of linear equations. Because they're true, that means that AX1 and AX2, both of them are equal to B. But that means I could subtract, and it also means that AX1 equals AX2. In other words, forget the B, it means that AX1 equals AX2. And if I subtract AX2 from both sides, and then factor out the A, which, because we learned, that's why it's so important that we learned that matrix multiplication is distributive. So we know that A times x1 minus x2 is equal to 0. Not the number 0, but the 0 matrix. Now, let's look at this matrix, x1 minus x2. x1 minus x2, that is a new column matrix. So let's just call that XH. H, of course, stands for Harry. No, I'm just kidding. H actually stands for homogeneous. Because if I have this is kind of, there's XH is kind of a solution to a homogeneous system of equations where AXH equals 0, meaning the 0 matrix. So, which is really what we're saying here. So if I have AX equals 0, or the 0 matrix, then XH is a solution to that. Well, this is going to be, so therefore, now here's where it really gets good and juicy here. If I let C equal any scalar, and I put in x1 plus CXH, Well, I could distribute. So that's going to be AX1 plus A times CXH. Now, I know that AX1 is equal to B, so I'm putting a big B there. And I know that I could factor out one of the properties of matrices multiplication is that I could factor out that constant. And so A times CXH becomes C times AXH. But I also know that AXH is 0. That was my whole supposition. That's what I get from the given already. And a constant times the 0 matrix is just the 0 matrix. And if I add a matrix, if I add a 0 matrix onto any other matrix, that means that I just get the original matrix. So what does this mean? It means that x1 plus some constant times xh is now a solution to ax equals b. But we said there's only either one solution or no solutions. Yet here we see, I'm sorry. So let me say it this way. We've shown that if there are two solutions, x1 and x2, that means that I could generate more solutions by just by taking my xh and adding constant scalar multiples of xh onto x1. And since there's an infinite amount of scalars out there, means there are an infinite amount of different possible solutions that I could make. And that's really what we're saying here. So, and just look at what it says: x1 plus, x1 plus cxh. Let me just raise this up here. x1 plus cxh is the solution of ax equals b for any scalar c. And there are infinite amount of scalars out there for C, and therefore there's an infinite amount of solutions to the system. And that's what we've shown. So we've shown that either there's no solutions, one solution, because both those things are possible. We know those things are possible. And that's it. Because if you have more than one, if you have two, once you have two, that forces you to have infinite. And that is awesome. Okay, now we're going to switch tracks and we're going to go to something called a transpose. A transpose, now these definitions are very fancy and, but basically what happens in a transpose is that we take a matrix and the rows of the original matrix become the columns of the new transpose matrix. So we're kind of taking a matrix and sort of flipping it around its diagonal. By the way, a transpose does not have to be a square matrix. It could be, we could do a transpose for any matrix, square or not. And but you see A11, A12, A13, dot 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 up to A1n, those same numbers are down here. A11, A12, A13, A1n. Let's look at some actual more concrete examples of transposes. So here we have, if my original A is 2, 8, my original B is this, my original C, my original D. So let's see what we got. Let's see what the transpose look like. So the transpose of A is this 2, 8, because that column and that row, are switched. For B, here's 1, 2, 3. Notice of B, my top row of B is 1, 2, 3, but in B transpose, my first column is 1, 2, 3. So the rows become columns. Here also, the row here of A is just 2, and now that's the column. The row here is 8, and now that's a column. That's what I'm trying to say. For C, when I transpose it, I get, now notice this is kind of cool. Notice that when I do the transpose of C, I want to get the exact same matrix. You see what I'm saying? If you look, the C here is 1, 2, 0, 2, 1, 0, 0, 0, 1, and C transpose is 1, 2, 0, 2, 1, 0, 0, 0, 1. When that happens, that the matrix and the transpose gives you the same thing, we call that symmetric, and that's the word right here on the side, symmetric. And you can see the symmetry. It's symmetric. This matrix is symmetric with respect to that main diagonal. And so here's a matrix D, and when I transpose it, I get this sucker right here. So notice, first of all, that D started as a 3 by 2, and the transpose became a 2 by 3. A started as a 2 by 1, the transpose became a 1 by 2. In other words, when I transpose it, the size like switches. So M by N, Mike by November, becomes November by Mike. By the way, I keep on saying Mike November, Mike for M, November for N, because when you say M and N, especially on a recording, it's easy to get confused. That's why I keep on saying that, so make sure you know what I'm trying to say. Now here is some properties of transposes. First of all, this one is pretty obvious. The transpose of a transpose is just the original matrix. Here, if I take a sum of two matrices and I transpose that sum, it would be the same as if I transpose each matrix individually and then add them up. So I guess you could say the transpose of the sum is equal to the sum of the transposes. That's another way of saying it. For number 3, we're saying if I have a matrix and I multiply it by a scalar and then transpose the whole thing, that's the same thing as transposing first and then multiplying everything by the scale. These things are actually, if you just draw these out, these are very, very obvious and easy to prove. This one is a little more subtle, the number 4. If I take a product and then transpose the product, that's going to be the same as transposing each thing individually and multiplying them, but of course in reverse order. And let's look at some fun things here. By the way, number 2 and 4, I'm doing it with sums, with just a sum of 2 things, but it could be sum of 3 things or more. And here this could be the product of many rows. So if I have a product ABC and transpose the product, that's the same thing as C transpose, B transpose, H transpose. So again, the transpose of the product is equal to the product of the transposes, but in reverse order. And okay, moving on. So let's give an example and see how this actually works. So again, this is not quite a proof, but sometimes when you give an example, you just get a better insight into it, and then the proof will kind of just make more sense. You'll see why it's true. Anyway, here's a matrix A, it's a 3 by 3. Here's a matrix B, that is a 3 by 2. And notice I can multiply AB, but I could not multiply BA because BA won't match up. But I could do B transpose, A transpose, because that's going to switch around the columns and rows and everything's going to work out. But let's just take it one step at a time. So here's matrix A, here's matrix B. I'd like you to multiply these two matrices and see that you get this as your result. Then when you transpose this guy here, 2, 1, 6, -1, -1, 2, you're going to get 2, 6, -1, 1, -1, 2. On the other hand, if I would just take B and transpose it, and I would just take A and transpose that, which is what I have right here, and then multiply these two guys together, which now this multiplication will work because I have a 2 by 3, here I have a 3 by 3. So the columns of the first matrix does match up with the rows of the second matrix. And now when I multiply this out, I will get 2, 6, -1, 1, -1, 2. But again, I want you to actually multiply it out, and I want you to see that this works with the matrix multiplication. Now, let's continue. What happens if I take a matrix and I multiply it by its own transpose? So whenever this is going to be, now this is an example, but it's actually going to be always true. If I take a matrix and then transpose it and multiply the two guys together, first of all, I will be able to do it because the columns and the rows and everything will match up. But also, the result is always going to be symmetric. So here's A transpose, and this is A times A transpose. It's easy to prove. It's always going to be symmetric, and that's pretty awesome. Pretty nice, good, awesome fact. This concludes 2.2. And I'm going to stop the recording now, and we'll see you next time in 2.3. If yes, you'll receive an email.